Join all my colleagues in giving you a very warm welcome to Princeton. I'm going to be talking about a new picture for the physics of scattering amplitudes, at least for some special theories, starting with n equals 4 super Yang-Mills in the planar limit in 4 dimensions. This is a subject that's been being developed from many different points of view for depending on when you start counting, sort of 20 or 25 years now. And from the particular point of view that my collaborators and I have been exploring for around 5 or 6 years now, it won't be possible for me in a 1-hour talk, and I promise it'll be a 1-hour talk, certainly to describe what's going on in any level of completeness. What I hope to accomplish in my 1 hour is to get across some of the motivation and the philosophy behind this line of work, and B, to at least tell you a few precise things, okay? A few precise things that are very simple to go in your head, and if you're interested in the subject, you want to think about related things. It's an extremely simple subject. It's just novel, but it's extraordinarily simple, and there's lots of room for simple and interesting thoughts. So I at least wanted to define what this gadget is with some precision. Okay, and indeed, this is work that's been ongoing for quite a number of years now, culminating in the paper with this title, written with Yaroslav Turinka, who's back there somewhere. Okay, so we all love quantum field theory. It's the foundation of all of our understanding of nature. And it was handed down to us by our intellectual ancestors in the early part of the 20th century as a combination of the two big revolutions of quantum mechanics and space-time, and more technically, trying to describe physics in a way that's both unitary and compatible with relativistic locality. So, in fact, the Q and the F in quantum field theory are really representing these two things. The Q, obviously, it's quantum mechanics. And in order to describe the interactions between particles in a way that's manifestly local, the only way that we've learned how to do it in a systematic way over the last 80 years is to combine, is not to talk about the individual particles, but to combine them into fields and to write down local interactions for the fields that we then integrate over all of space or all of space-time in a Lagrangian or pathinical picture of what's going on. Okay, so unitarity and locality are the prime movers of our drama, and it's difficult to make physics manifestly compatible with both of those principles. That's why this entire beautiful, intricate structure of quantum field theory, as we've been used to it, has been invented. Now, since locality and unitarity are going to be so important, I want to pause for a second to tell you something that many of you know, but to tell you a little specifically how locality and unitarity are actually encoded in physical scattering amplitudes. So we're going to be talking about scattering amplitudes of gluons, gravitons, it doesn't really matter, but for this talk we'll be talking about gluons. And let's say that, and we know how to do this, right? Since time immemorial, since Feynman and Dyson and Schwinger, we know one way of doing the calculations is to sum up tons of Feynman diagrams. We'll talk about it a little more in a second. But let's say someone came along and said, I did it. I don't tell you how I did it, but I did it. Here's the answer, right? Here is the answer for the amplitude as a function of the momenta and the helicities of the particle. Tuck, there it is. How do you know whether they're telling the truth? Okay? Are you going to go sum all the Feynman diagrams yourself? That's kind of a waste. They did all this work in principle, right? So you just want to check that they're right. Is there a way you can check that they're right? How is the fact that the answer is local and unitary reflected in the actual function, right? And the way it's reflected in the actual function is in the presence of certain kinds of singularities. In fact, locality tells you where the singularities of the amplitude are. And unitarity tells you what happens as you approach those singularities. So locality tells you where the singularities are, and unitarity tells you certain factorization or cut properties as you approach those singularities. And we'll review it in a second, but just conceptually something to keep in mind is that the entire purpose in life of Feynman diagrams is to make the presence of these singularities and what happens to the amplitudes near these singularities as manifest as possible. So let's do an example at tree level. Okay? So let's say I want to calculate 2 to 4 gluons at tree level, so I draw all these Feynman diagrams. Okay? We know that and we'll see in a second, we're going to get a horrendously complicated looking result if we actually write all the expressions down. But despite the fact that the result is complicated, there is one thing which is totally obvious in this way of writing the answer. Where are the poles? The only poles that you can have, the only place where there are anything in the denominator, are in the propagators. And the only things that appear in the propagators are a sum of a certain subset of the external momenta, right? So the only poles that you can possibly have look like 1 over p squared, where p is some sum of the subset of the momenta. That's locality. So if someone comes along and says, I summed up all the Feynman diagrams, and you stare at the answer, and it has a pole that looks like 1 over p squared q squared minus r squared t squared, they're lying, right? That could never come from summing Feynman diagrams, and it's not local. Okay? That kind of pole back in position space means that the only kind of singularity that you can have is when a bunch of particles come together here, propagate over a very, very long distance, and then something happens on the other side. Okay? So that's locality, where the poles are. Unitarity is encoded in what happens on those poles. As you approach this pole, it's not just that the amplitude has a singularity, but what multiplies a singularity is a very simple interpretation. First, this happens on this side. The sum of the momenta that's going on shell is interpreted as a physical particle. So you produce this intermediate particle that propagates over a long distance and then decays out the other side. Okay? So unitarity tells you that on the pole, the amplitude has to factorize into on-shell lower particle amplitudes, sort of summed over all the possible helicities of the particles that can propagate there. Okay, so that's locality is where the poles are, unitarity is what happens on the poles reflected in factorization properties. Okay, so, and as we see, Feynman diagrams make that completely manifest, but they make it manifest at a price. And the price is the familiar redundancies that we talk about in quantum field theory. Even before getting to gauge theories, even for simple scalar field theories, we have field redefinitions. We can't uniquely associate fields with the particles that we are colliding. We can do arbitrary field redefinitions, completely change what the Lagrangian looks like, and yet have exactly the same scattering amplitudes. It gets much more costly when we start talking about particles with spin, because of the famous difficulty that a massless spin 1 particle has 2 helicities. Okay? If we're trying to describe the 2 helicities of a massless spin 1 particle, how are we going to do it, right? We're grouping these guys into fields. That's the whole idea. So there's got to be a polarization vector associated with them. And we pretend there is such a thing as a polarization vector epsilon. But epsilon has 4 components. So how do we get epsilon to describe the two helicities? Well, we can try imposing a Lorentz invariant constraint on it, like epsilon dot p equals 0. That's fine. That gets us from 4 to 3, but that's still not enough, right? There's only two helicities. And so what we're forced to do is really introduce a new idea, that the state is not uniquely associated with the polarization vector, but with an equivalence class of polarization vectors that differ by something proportional to p mu. There's another way of saying this, which is that when we calculate amplitudes using Feynman diagrams, we don't actually compute an amplitude. We compute something which is a Lorentz tensor. If we have a spin 1 particle, it's something that has a bunch of indices, m mu 1 through mu n. Okay? The actual amplitude is not a Lorentz tensor. The amplitude has the property that if you do a Lorentz transformation on the momenta, you pick up a little group phase acting on the external states, a phase e to the plus I h theta or e to the minus I h theta for a particle of spin h, right? Or e to the I h theta for helicity h. So So what we pretend is that there's such a thing as a polarization vector, which when I dot it into, the polarization vector has a Lorentz index, I dot it into the Lorentz indices of what I calculate with Feynman diagrams, and that composite object transforms correctly under the little group. But the difficulty is that there's no such thing as a Lorentz invariant set of polarization vectors, precisely for this reason. There's no way we can pick out the 2 degrees of freedom in a Lorentz invariant way. If you say, what are you talking about? I know what I'm doing. I have a particle moving in the z direction. Its momentum is 1, 0, 0, 1. The polarization vectors are 0, 1 over root 2, plus minus I over root 2, 0. I'm done. Those are the polarization vectors. That's fine. But if you do a rotation, a boost, and a rotation back, such that the momentum comes back to itself, you will not find that the polarization vector returns to itself with zeros in those components anymore. Okay? It will have something non-zero in the first and the time and the z component, and it will differ from the original one by something proportional to p mu. Okay? There is no Lorentz invariant way of choosing the polarization vectors. The only Lorentz invariant object is the equivalence class of polarization vectors, and that's the price. So we have to have these gauge redundancies in order to describe the physics of massless spin 1 particles and higher spin particles in a way that's as manifestly local and unitary as possible. And the result of this price is this mess, if you actually try to do a calculation for 2 to 3 gluon scattering. 2 to 2 gluon scattering, you put on problem sets. The fact that all of you are here means that you've managed to somehow pass that threshold, okay? So, but 2 to 3, you would not be able to pass threshold unless you're crazy, in which case, please come to Princeton as a graduate student. You know, we'll have to deprogram you, but still, you'll have some very special skills. No, but it's a complete mess, right? So that's 2 to 3 gluons, there's 25 pages that looks like that nonsense. And that's what you get if you try to make the result manifestly local and unitary. Now, you might think the result looks complicated because it is complicated. Not every question in physics is guaranteed to have a simple answer. And part of the chauvinism of us in theoretical physics, in this part of the field anyway, is to define as uninteresting the questions that have very complicated answers as only as interesting the questions that have very simple and beautiful answers. Okay? So you might just think this is a grungy, terrible process. Someone's got to compute it for some practical reason. In fact, people have to calculate these things. They continue to have to calculate these things to make predictions for backgrounds and hadron colliders. So some poor schmo has got to go do these calculations, but the result is complicated. It looks complicated because it is complicated. Physics has a wonderful way of rewarding morally correct behavior, however. And so the people who have to go do this for this bread and butter, at least the particle physicists' bread and butter reason, found an incredible surprise in the late 80s that these 30 pages of algebra collapsed to a single term for the actual amplitudes. Okay? So that's already a hint back then. It wasn't universally thought of back then as the tip of a big iceberg. Today we know it's a tip of a very big iceberg. But it's already a hint there's something wrong with there's something wrong with making locality and unitarity as manifest as possible. Okay? The results look complicated even though they turn out to be simple. Now this keeps on going. So another qualitative aspect of this tension is that there's a tension with symmetries. Okay? Let me illustrate this tension with symmetries by giving an example of 2 different amplitudes. Here's the amplitude for phi cube theory. Okay? Just a 4-particle amplitude for phi cube theory. You can, I think, recognize it. It looks like mu squared 1 over s plus 1 over t plus 1 over u. Okay? And if I hand you that amplitude, you have no difficulty seeing that it's local and unitary, right? The poles are at s, t, and u goes to 0, and it's obvious that it factorizes on those poles into the product of the 3-particle amplitudes. Now let me write down what the scattering amplitude is for gravity. Okay? And in fact, let me write it down for supergravity, for the maximally supersymmetric supergravity theory. Okay? We're all familiar with the fact that the amplitudes have a delta function for momentum conservation in front of them. If the theory is supersymmetric, there's also the superpartner of momentum conservation, the delta function for the supercharge, if you like. So let's factor that piece out as well. Okay? So obviously, so there's a momentum conserving delta function I haven't even written. There's a delta function for the supersymmetry, and once you factor that piece out, what's left looks like g Newton over STU. Now, isn't that interesting? It's over the product of ST and U. It cannot possibly be written as a sum of 1 over s plus 1 over t plus 1 over u. Okay? This is the one-line proof that there's no such thing as an off-shell superspace for maximal supersymmetry, either for n equals 8 supergravity or for n equals 4 super Yang-Mills, where the analogous statement is true. Imagine there was such a thing as a super-duper off-shell superspace. Then its Feynman diagrams, whatever they were, each term would be manifestly supersymmetric, so each term would come along with that delta function for supermomentum conservation, but there would be a piece for the S channel, the T channel, and the U channel. That's impossible. It looks like 1 over STU. So that tells you that it's impossible to have any formalism which is manifestly local and manifestly maximally supersymmetric at the same time. Okay? This is something that you're familiar with from many guises. It's a strange fact about supersymmetry. Unlike other symmetries, when you have more and more supersymmetry, the Lagrangians look more and more complicated. The superspaces are more and more insane. You know, n equals 1, again, you're all here, so you manage to pass that threshold. N equals 2, unless you're a crazy Russian who really likes harmonic superspace. N equals 3, you're a super duper crazy Russian, okay? And n equals 4, there is none, okay? This is the reason why there is none. But it should bother you. It's a little strange that the more and more supersymmetric the theory becomes, the harder and harder it is to make it compatible with manifest locality. Okay? So there's a tension with symmetries. Now, there's a tension with obvious symmetries. There's even more of a tension with hidden symmetries. The tension is that they're hidden, so you don't see them. So famously, super Yang-Mills amplitudes have a symmetry. At tree level, the Yang-Mills amplitudes for the gluons are the same as whether it's supersymmetric or not. So at tree level, this statement even for non-supersymmetric theory. At loop level, it's only true for theories with maximal supersymmetry. But maximally supersymmetric theories have this famous symmetry of dual conformal invariance. Okay? Now, what's dual conformal invariance? Well, if you imagine taking the momenta for the particles and just arranging them end to end to make a 4-dimensional or a d-dimensional polygon, momentum conservation is a statement that this forms a closed polygon, and the edges have to be null. So we have this null polygon. And the experimental observation, which has now been proven, is that these things are conformally invariant under conformal transformations in this X space, in this funny momentum space. Okay? If we write the momenta as a difference between two coordinates, there's conformal transformations in this space. That's not the ordinary conformal symmetry. Okay? This is conformal symmetry in sort of momentum space. Now, the remarkable thing is that while Yang-Mills theories are conformal in 4 dimensions, they're not conformal in higher dimensions. Okay? So they don't even have the obvious symmetry only exists in 4 dimensions. But they're dual conformally invariant in any number of dimensions. Okay? So there's a hidden symmetry, at least in the planar limit. This is only true in the planar limit. But in the planar limit, there's a symmetry which is completely invisible in the Lagrangian in any number of dimensions. In 4 dimensions, this symmetry, together with the ordinary conformal symmetry, close into an infinite dimensional symmetry of the Yangian of the conformal group SL4 or SL4/4 when it's supersymmetric. And that infinite dimensional symmetry, again, is completely invisible in the Lagrangian. Okay? So that's just what I said. Okay, so well, all of this might suggest that, at least in perturbation theory, we can go back and try to think about what the physics of scattering amplitudes is, instead of, from the very beginning, insisting on describing the physics with fields, local fields, and gauge redundancies, and so on, to see if it's possible to directly determine what the answer is from these general principles of locality and unitarity. I'm going to pursue this line of thought for around 5 minutes, because it's not the philosophy of the rest of the talk. Okay? But it's been a very, very fruitful way of thinking, and it's continuing to march along on a number of fronts. So I want to at least review how it's supposed to work. So let's begin by talking about how to think about massless particles in a convenient way. Okay? So if a particle is massless, well, for any 4 momentum, we can, in 4 dimensions, we can conveniently turn it into the 2x2 matrix by dotting to the Pauli matrices in the usual way. And the fact that the particle is null tells you that the determinant of this 2x2 matrix is 0. P squared is the determinant of that matrix. The fact that 2x2 matrix has 0 determinant tells you that it has rank 1, so we can write as the outer product of two 2-dimensional vectors. So lambda and lambda tilde are just ordinary 2-dimensional bosonic vectors. Okay, so, and beautifully, the scattering amplitudes are functions of lambda and lambda tilde. Okay? There's no polarization vectors needed. There are functions of lambdas and lambda tildes, and the helicities of the particles are reflected in the homogeneity, the weights that the amplitudes pick up when you rescale lambda by t and lambda tilde by t inverse. You see, if I rescale or rephase lambda and lambda tilde oppositely, that leaves the null momentum invariant. So what does that remind you of? Some action on a null momentum that leaves it invariant but gives you a phase. That's precisely the action of the little group. Okay, so the action of the little group is simply reflected in the weights that the amplitudes have under rescaling lambda and lambda tilde by opposite amounts. Now, if we go from, and now Juan mentioned this yesterday in a closely related language. The three particle amplitudes turn out to be completely determined by symmetries, by Poincare symmetry, up to an overall constant. It's a very simple exercise that I encourage you to do, that if you have three particles, just three-particle momentum conservation is possible to be satisfied in only two ways. Either the lambdas are all parallel to each other, these two-dimensional vectors, or the lambda tildes are all parallel to each other. That's reflected in the statement Juan said yesterday that there's no kinematic invariance. So k1 dot k2, all of these things are equal to 0, and k1 dot k2 is the product of the lambda 1 and lambda 2 contracted with an epsilon symbol, the lambda tilde 1 and lambda tilde 2 contracted with an epsilon symbol. So the fact that all those kinematic invariants are 0 tells you that either the lambdas contract to 0 or the lambda tildes contract to 0, and so either the lambdas are all parallel or the lambda tildes are all parallel. And that tells you that since only lambdas or lambda tildes can appear here, in fact, the powers that can appear are completely determined by the weights. Okay? So once you give the helicities of the particles, you know exactly what can appear here up to an overall constant. So that's beautiful. Poincare symmetry completely determines the structure of the three-particle amplitudes. So far, we could talk about three particles or 27,000 spin particles. Okay? But now something happens when we try to build consistent four-particle amplitudes. So let me just do a little example. Let's try to build a consistent theory for a single particle of spin s, curly s. Okay, so the whole world contains a single spin curly s particle.
Are you going to explain what the angle brackets are?
Yes. I think I had it on a slide which I deleted in the attempt to stay within my self-enforced bounds here. So thank you. So the angle brackets denote contracting lambda 1 and lambda 2 with an epsilon symbol, and the square brackets are contracting the lambda tildes with an epsilon symbol. Those are the only invariants we can have. Those are the only Lorentz invariants we can have. I apologize. Okay. So let's try to write down a consistent four-particle amplitude now. Let's say for that helicity configuration. I'm going to pull out this factor, which takes care of all the weights. So what multiplies it is just some function of s, t, and u. Okay? All right. Now, so it's Lorentz invariant manifestly. But unitarity tells me the only poles are when s, t, or u goes to 0. And furthermore, it tells me what has to happen at those poles. It has to factorize in this way. Now remember, we know precisely what these things look like. And it's two lines of algebra to translate the known statement here into a property for this function of s, t, and u. And it's the following very simple property. F of s, t, and u has got to go like 1 over s times g squared over t to the spin in the s channel, similarly for the t and the u channels. So now we have a math problem. Can you find a function of s, t, and u, symmetric in s, t, and u, such that its only singularities are when s, t, and u goes to 0, and this is what it does on those singularities. Okay? So this is the homework problem for you. A very simple homework problem. Hint, don't be scared of the fact that it's two complex variables. Just explore it in a one-dimensional space, okay, and think about Cauchy's theorem. But it has a surprising answer. It's almost impossible. There are almost no functions which have this property. In fact, only the case little s equals 0 and little s equals 2 work. Little s equals 0, and not only do you find they work, you also find what the function is. So the function is 1 over s plus 1 over t plus 1 over u. That's known as phi cubed theory. Or g squared over s to u, that's gravity. So that's why we can't have spin 3, spin 17, you know, that there's... we didn't write down a Lagrangian. We didn't think about conserved currents. There's all sorts of other ways of arriving at conclusions like this from a more standard point of view, but this is a very sharp way of getting it just from directly imposing the constraints of locality and unitarity. Okay, that's great. So we've discovered that if we have a single particle of spin s in the universe, it can only be spin 0 interacting with a cubic coupling. It can be spin 0 or spin 2. All right, what about spin 1? Well, it's a very, what about Yang-Mills theory? It's very important that it was a single particle there, okay? And it's a good thing, it's a very good thing that we found that we couldn't do it with spin 1, because if we could have done it with spin 1, that would have been what the amplitude is, okay? For minus, minus, plus helicity. And you'll notice that this is because that's and contracted with an epsilon symbol, this is anti-symmetric in switching 1 and 2. So had we found a consistent theory for a single massless spin 1, it would have violated spin statistics. So spin statistics also comes along for the ride here, okay? So the only way we can do it is if we have many of these particles, okay? So if we have many of them, then let me just call the strength of that interaction FABC. That's just a label for what the interactions are. You repeat the same machine, you turn the crank, and you discover that it's only possible if the FABC satisfy the Jacobi identity. Okay? And so you start discovering what the consistent theories are. In fact, if you finish this exercise, you find that Poincare invariance plus consistent factorization, just of the 4-particle amplitude, tell you that the only consistent theories of interacting massless particles are the ones that we know of, spin 0, a half, 1, 3/2, and 2. And you discover everything about them. You discover supersymmetry, you discover that the spin 2 particle is unique, it's GR at long distances, and so on and so forth. Okay, okay, so now, this kind of observation is generalized in what you can think of as the modern version of the S-matrix program. Okay? The old S-matrix program was to not think about Lagrangians and path integrals and quantum field theories directly, but to try to impose the constraints of locality and unitarity, causalities, they called it causality and unitarity, to determine the amplitudes. Okay? And anyway, they had lots of famous difficulties, and let's not, I can tell anyone who's interested about the analogies between then and now at greater length at another time. But the basic philosophy is to exploit locality and unitarity to directly determine amplitudes without using Feynman diagrams. And so this is to take locality and unitarity as given and use them in as efficient way as possible to determine the answer. And there's many words that have been, and important ideas that have been associated with this strategy over the last 20 years. There's a beautiful idea pioneered by Zvi Byrne, Lance Dixon, David Kossauer, Dunbar, and others to use not just the familiar constraints from unitarity cuts, but something called generalized unitarity to finer singularities of the scattering amplitudes or the integrands of the scattering amplitudes to determine what they are without Feynman diagrams. In the hands of Freddie Cacciazzo, this was further sharpened to the beautiful and very, to us, important idea of leading singularities. I won't have much time to talk about, but that's really thinking about the most singular possible part of the amplitude and understanding it well and using it to determine, using locality and unitarity, what the answer is. Going all the way back to tree level, probably the most important of all of these developments from our point of view were these beautiful recursion relations by Brito, Cacciazzo, Feng, and Witten for calculating higher point tree amplitudes by sewing together lower point tree amplitudes, not using Feynman diagrams again, but just directly using on-shell objects. Okay? So, and this program is blossoming, and there's all kinds of more and more things like this going on all the time. So, to use locality and unitarity to efficiently determine what the amplitudes are. Okay? And at least the part of this research trajectory that my collaborators and I have been on, a big original part of it was just to make some small contribution to this program. But my own motivation for getting into this business were exactly the opposite of this. Okay? I just want to spend 2 minutes talking about this because it's really almost the opposite. The motivation is something else entirely. The motivation has to do with all sorts of things that you've all heard about, but I won't have time to go through in detail. But we know that for various deep reasons having to do with gravity and cosmology, certainly the idea of space-time should be emergent. And it's possible, this is This is certainly not universally agreed upon. Probably, maybe no one agrees with it. But I think everyone would agree that thinking about how to apply quantum mechanics to the entire universe, especially to accelerating universes or to the eternally inflating universes that one encounters in various attempts to try to understand the smallness of the cosmological constant, invoking the landscape of string theory and so on, certainly make it incredibly confusing to apply quantum mechanics. It's not obvious what the correct quantum mechanical observables are. So it's possible that we have a big step ahead of us. We have to understand both emergent spacetime and perhaps even quantum mechanics, not to be wrong, not to be modified, but to be extended somehow, such that in situations where today we don't know how to extract unambiguous quantum mechanical predictions, there's some other structure that would tell us what to think about, what to compute. Okay, so how can we attack a question like this? Well, the most obvious thing to do, and what most people do, quite rightly, is to think about questions where these issues come up at order 1. These difficult gravitational cosmological issues come up at order 1. So they try to make sense of singularities. They try to make sense of what happens inside a black hole, what happens, how to make sense of the measure problem in eternal inflation, and so on. Okay? But there is a sort of orthogonal strategy that may go nowhere for these set of problems, but at least has a historical precedent. So we've had to make these kind of transitions before. We went, after all, from classical to quantum, where we had to give up something huge. We had to give up determinism. And you might wonder, if you just told a classical physicist 200 years ago that in 200 years they would have to give up determinism, how would they react to this news, right? They would want to do something about it. They might want to write a paper before the next person finds out about it, right? So it's a big thing that's coming up. And they could try to guess what the next physics is, and there's no way in heck are they going to make the correct guess. They're not going to invent Hilbert spaces and wave functions and all the rest of it. They might do stupid things like add stochastic terms to Newton's laws, which is not the right answer. The right answer isn't stupid like that, right? It's not some just violation of determinism in a dumb way. The right answer is much more subtle, okay? So if they become convinced they can't just jump to the right answer, they could take a more conservative attitude, but maybe a more fruitful one, which is that if determinism isn't really there fundamentally, then it's not even really there in Newton's laws. Of course it's there. Of course it's there as a fact. But there must be some way of thinking about Newton's laws where the classical determinism isn't hardwired into the description of how you think about it, because it's not really there. Whatever the next way of thinking about it is, its correspondence limit can't land you on a way, can't just become deterministic all of a sudden. It must land you on some new way of thinking about classical mechanics that's not manifestly deterministic. Does such a way of thinking about classical mechanics exist? Of course it does. It's the principle of least action. And when we all learn about it, we get this funny feeling, right? Does a particle really sniff out every path it can take from A to B and choose the one that extremizes the action? It doesn't feel like it's deterministic. Of course, it's just a rewriting of Newton's laws. But the fact that it seems to have to dislodge determinism from its fundamental place in the description of the physics is preparing you, putting you in the right mental place and preparing you for the transition to quantum mechanics. Or, said even more mildly, purely from the point of view of a classical physicist, it would appear strange that there are these two radically different ways of thinking about classical physics. Manifestly deterministic, not so manifestly deterministic. What explains this mysterious feature of classical physics? The existence of quantum mechanics explains it. The world isn't classical, it's quantum mechanical. And the right way of thinking about it doesn't land you on Newton's laws, but it lands you on this other way of thinking about Newton's laws that's not manifestly deterministic. Okay, so that suggests a strategy for attacking this question of emergent spacetime is to first figure out some way of reformulating what quantum field theory is, where we eviscerate locality and unitarity from its fundamental role in our thinking about the physics, and somehow see them arise as emergent phenomena. And as derived phenomenon, maybe emergent has too much baggage, but somehow it's not sitting there in the formulation. You see that the answer is local and unitary in a different way. And here I want to stress the difference between this attitude and the S-matrix program, right? even the modern version of the S-matrix program, we don't want to just use locality and unitarity to get the answer. Okay? We want to see locality and unitarity arise from a different starting point. Said yet another way, we're trying to find a different question to which the scattering amplitudes are the answer. Not the question of evolve from the past to the future and see what you get. But it's the answer, this mathematical function is the answer to a different mathematical question, and hopefully a natural, a nice question, and then we can understand why the answer to that question has the features that allow us to interpret the results as being local and unitary. All right, so this is strategy 1 is reformulation. Strategy 2, the second part would be to find a natural deformation somehow, the analog of going from the principle of least action to the path integral. Okay, so that's God knows, 2 centuries strategy. Who knows how long it'll take? In fact, step 1 divides into step 0, which is already taking a long time, which is to understand how this works for planar n equals 4 super Yang-Mills, the sort of simplest possible theory we can imagine trying it on. Certainly, if there is a whiz-bang new way of thinking about things, we had better see it already for n equals 4 super Yang-Mills. The danger is that n equals 4 super Yang-Mills is so special and nice that what we're seeing is just a mirage. It's just special to n equals 4 and won't generalize. Okay? That's a danger that we're going to have to live with for now. And anyway, we start how we can. Okay? Okay. So reiterating what the goal is we want to find a new picture for scattering amplitudes where the words space-time, Hilbert space, Lagrangian, Hamiltonian, path integrals, gauge symmetries, and so on don't make an appearance. Okay, now, in the course of these investigations a number of years ago, there was a sort of a vague picture that started emerging for what this new question might be that the amplitudes were the answer to. And the picture was the following. Imagine you're given all the external data, all the momenta of all the gluons, all the helicity. You're given the external data. That this data defines a region in some space, okay? And that the amplitude should be thought of as the volume of that region. People had found all kinds of different ways of representing the amplitude. No one of them, for example, using these recursion relations at tree level, at loop level. Okay? There are all sorts of beautiful ways of writing the answer. They're written in terms of very nice building blocks. But there was no preferred way of writing the answer. You could solve the recursion relations in many different orders, many different ways. They didn't come out in one specific form. So that and a number of other things were a rough clue that we should think about the scattering amplitudes as the volume of a region, and all the different ways of computing the amplitude were equivalent to computing this volume as a triangulation. Okay? You would triangulate the space in lots of different ways, and each triangulation corresponded to one of these known ways of computing the amplitude. Maybe other triangulations would correspond to others. So that was a sort of a vague picture that we were hoping to find. And associated with this vague hope was that if we understood what this picture was, we would see all the symmetries of the problem, for example. In n equals 4 super Yang-Mills, we'd see the conformal and the dual conformal symmetry. We'd see the whole Yangian symmetry. And all of that would obviously only be possible without paying fealty to one space-time or the other space-time. So we would have to somehow see locality and unitarity as derived features. Okay? So that's what we want to do, and that's what I will then tell you about in the last part of the talk. So just before getting there, let's just talk a little bit more in detail about kinematics. I promise you I'll at least try to tell you a few sharp things. Okay, so we're talking about the scattering amplitudes for gluons. So these things start off life as being functions of momenta and helicities of the gluons, and they have color indices. The first thing we do is strip off all of these color indices. Imagine you computed a bunch of Feynman diagrams. There's a lot of FABCs everywhere. Everywhere you say an FABC, you write it as trace TA, commutator TB, and TC, and then you do an orgy of moving traces around, the T's around by expanding them out. And at the end of the day, all the dependence on the color factors comes out as overall trace factors that sit out in front. In the large n limit, all we get are these single traces. Okay? So in the planar limit, we just have these pieces with single traces. Okay? So what multiplies, so if it was 4 particles, there would be a piece that's trace A1, trace TA1, TA2, TA3, TA4, multiplied by m of 1, 2, 3, 4. There'll be another piece, trace TA2, TA1, TA3, TA4, multiplied by m of 2, 1, 3, 4, and so on. Okay? So you just sum over all those permutations up to cyclic ordering, because these traces are cyclically ordered. So the thing which multiplies here is, it's called the color-stripped scattering amplitudes. It's a manifestly gauge-invariant object. Now, in a supersymmetric theory, instead of labeling things with, first, instead of labeling things with momenta, we label them with these lambdas and lambda tildes. And secondly, instead of labeling them with all the helicities, we group the helicities together into a Grassmann coherent state. So we have Q's and Q tildes as symmetries as well. And so we might as well diagonalize all the symmetries we can. We diagonalize the translations by going to momentum space. And we can diagonalize Q or Q tilde. They don't anti-commute with each other, so we have to make a choice. So we can diagonalize, let's say, Q tilde. And so the states are labeled by eigenstates of Q tilde, which is a Grassmann coherent state. These eta tildes are just Grassmann variables, and they just correspond to a particular linear combination of all the helicity states. The positive gluon, eta tilde times the fermions, eta tilde times the scalars, and so on. Okay, so this is just a nice way of packaging all the helicities together. Okay? Now, this variable k, or k tilde, the amplitude is a polynomial in these Grassmann variables. It either has no eta tildes, or 4 eta tildes, or 8 eta tildes. They come in multiples of 4 because we have 4 supersymmetries. And this k tilde counts how many eta tildes there are. 4 k tilde eta tildes. It also corresponds in components to that part of the superamplitude that has k tilde negative helicity gluons. Okay? And finally, we strip off the overall momentum conservation, the superpartner of momentum conservation, and another factor that gets rid of all the helicity weights of the particles. And what we're left with is a function of the same lambda, lambda tilde, and eta tildes, which another little small but important algebraic manipulation converts this function of these variables lambda, lambda tilde bosonically into, so here are two two-dimensional vectors, and they're grouped together in another four-dimensional vector. Okay? So I take lambda, lambda tilde. I don't quite put lambda and lambda tilde together in a four-dimensional vector, but some linear combination. But I have a new four-dimensional vector from which I can reconstruct the lambdas and lambda tildes. The little group action here is just rescaling the z's homogeneously. So I just take z and I multiply by any constant times z. So the z's are four-dimensional vectors up to rescaling. You can think of them as points in a three-dimensional projective space, and they're known as momentum twistor variables. Okay. So that's now the goal. These guys, this mnk of z, you can calculate many, many ways. You can calculate using recursion relations, you can calculate using integrability methods, you can calculate using all sorts of different ways. But the goal is to understand a new question that this mnk is the answer to. Okay? And what I'm going to spend the last 15 minutes telling you about is what that question is. So we found that we can think of m and n and k and at L loop order as being the volume of a certain object that depends on the external data z and the same nk and L. And this a, nk, and L of z we call the amplituhedron. The choice of the terminology is that this is something that looks like sort of an intricate shape in a high-dimensional space. So it's not really a polyhedron, but there's all sorts of things that are called hedrons in this business, so we decided to call it hedron anyway. If it's anything, it's more like a polytope than a polyhedron, but amplitope sounds even stupider than amplituhedron. Okay. So now I'm going to switch gears for much of the rest of the talk. You can completely forget about. So now we're going to forget about physics for a little while, and just explore an interesting mathematical object. Okay. You'll probably immediately complain. It's just too ridiculously simple. Surely this is known to mathematicians for hundreds of years. And I think there's absolutely no reason this couldn't have been invented by mathematicians 100 years ago. Okay? Absolutely no reason. There's probably it's a funny historical accident that thinking about these things was delayed, was stopped in the late 1800s and was picked up again by mathematicians just in the late 1990s and early 2000s. Okay? But just to give you a roadmap for where we're going, everything is going to begin by thinking about a triangle, thinking carefully about the idea of a triangle and the inside of a triangle. So we'll think about the triangle for a while, and we'll generalize a triangle into one object. Okay? The generalization of a triangle into a slightly bigger space will be something known as the positive Grassmannian. I'll explain what all these things mean in a second. But this is one direction of generalization that our mathematician friends, as I said, had undertaken, and they had a very nice understanding of this the structure, this rather beautiful structure of a positive Grassmannian already by the mid-2000s, okay? 2006 to 2007 or so. All right, and this object already had a role to play in connecting with scattering amplitudes, an intermediate role in the bigger picture where they fit into the amplituhedron. Now, there's a second generalization of triangle, which is to go from a triangle into a polygon. Okay? And so then we'll spend some time thinking about that. And then if we do the same thing to the polygon, lift the polygon into the Grassmannian, the same way we lifted the triangle into the Grassmannian, that will give us the first example of an amplituhedron. Okay? So the generalization of inside of a polygon into the Grassmannian is the first instance of this amplituhedron whose quote-unquote volume calculates all tree amplitudes. Okay? So this object will be associated with all the tree amplitudes of the theory. Now, what about loops? What about quantum mechanical effects? Well, if you take this object and just geometrically think about how you would hide pieces from it, you would hide particles, you find there's essentially a unique way of hiding the particles. It doesn't introduce arbitrary extra structure. So you pursue this idea of hiding particles, and the idea of hiding particles gives rise to another geometry whose volume calculates all the loop amplitudes. Okay, so let me tell you, at least sketch out how this works. So let's think about the inside of a triangle. Imagine you're given 3 points just on a plane, z1, z2, z3, and you want to think about all the points that are inside the triangle. Well, a convenient way of doing it is to imagine that those points have masses c1, c2, and c3, and that you're going to, you just take the center of mass, right? So the center of mass is obviously inside the triangle, and if you scan over all the possible masses, you scan over all the points inside the triangle. Now, if we wrote this like in high school with little vector signs on these things, it would be y vector is c1, z1 plus z2, z2 plus c3, z3 over c1 plus c2 plus c3, right? That's the center of mass. So let's instead think of this projectively. So projectively, we now think of these as three-dimensional vectors up to rescaling. And now projectively, the same statement is saying the inside of the triangle is all the points y, which are just a combination of c1, z1 plus c2, z2 plus c3, z3. Now we don't have to divide by c1 plus c2 by c3 by hand. That's just taken care of by the projectivization. Okay, so the inside of a triangle in P2 is all points of this form, c1, c2, c3 mod GL1, mod overall rescaling, with the additional proviso that all these c's are positive. So that's where the positivity enters. Being on the inside tells you that all these c's are positive. Now we can generalize this to a simplex in the obvious way, which is of c1 up to cn mod GL1 with all the c's positive. That's the inside of a simplex. But now comes a generalization to the Grassmannian. So another way of thinking about c1 up to cn mod GL1 is it's just some n-dimensional vector, right? Up to rescaling just means it's a line in an n-dimensional space. So if you give me c's mod GL1, it's just a line in an n-dimensional space. I can generalize a line in an n-dimensional space to a general k-dimensional plane in an n-dimensional space. Okay? If I go from a line in n dimensions to a k-plane in n dimensions, now I'm talking about the Grassmannian. GKN is the space of k-planes in n dimensions. How do I give you a k-plane in n dimensions? Instead of giving you a bunch of numbers modulo GL1, I give you a bunch of k-dimensional vectors modulo GLK. Okay? You think of this as a k by n matrix. The top row, the second row, the third row, the kth row give you k n-dimensional vectors whose span gives you the k-plane. And you mod out by GLK because GLK is just giving you a different basis for the same plane. Okay, so we're going to generalize now from projective space into the Grassmannian. But what should the analog of positivity be? We can no longer say that all these we can't say that all the coefficients of this k by n matrix are individually positive. That's not invariant under k by k linear transformations. The only thing that we can do, the only thing that is invariant under k by k linear transformations are determinants taking k of the columns of this matrix and forming the determinant out of them. So those are the so-called minors of this k by n matrix. I take any k columns, I take the determinant, that's what this little bracket means, and I say all these determinants are positive. That's the only analog of positivity that's the only analog of the notion of inside I can come up with. Now already I have a problem because these guys have an ordering. So I can't say all the minors are positive. I can't say 137 is positive and 173 is positive. So I have to also order the columns. Okay? I give an ordering for the columns. And having fixed the ordering, I declare that all the minors in that ordering are positive. So I just define the object in one line here. This is the positive Grassmannian. But it's a much, much richer space than a simplex. It should be obvious that it's much richer than a simplex. These are nonlinear conditions, and the geometry is much more intricate. Okay, so let me now move on. So that's the positive Grassmannian. Now let me move on to talking about polygons. So what is the inside of a polygon? Let's say again I have n points, z1 through zn, and I want to talk about the inside of the space that has the z's as vertices. Already I have a problem that if the z's are completely randomly distributed, there is no particularly canonical notion of the inside of the region defined by the z's with those z's as vertices, right? Just imagine it's drawn in some absolutely horrible shape. What you should mean by the inside is not obvious. So for there to be a nice inside at all, they have to be organized nicely, okay? And so what we can imagine is that they're organized in the shape of a convex polygon. So imagine that the z's are a convex polygon. Now, obviously the notion of the inside is good. Okay, so how can I, if you just give me the z's, how can I decide if they are convex or not? Well, you could draw them and just stare at it. But let's say you wanted to tell Mathematica. How does Mathematica check if these guys are going to be a convex polygon or not? Well, it's very simple. You see, if it's convex, it means that all the ordered triangles in this picture all have the same sign of their area. Okay? The area of the triangle, the high school formula for the area of the triangle is just the determinant of 1z1, 1z2, 1z3. And that's just this minor, z1, z3, z7, for example, right? So notice that in order for the polygon to be convex, all of these ordered minors, now made out of the external data, have to be positive. Okay? So it's another notion of positivity. Now for the external data. Okay? Okay, great. So now I make sure the external data is positive, so all these ordered minors are positive. And now all the points on the inside of the polygon are just a linear combination of this positive external data with positive coefficients. Okay? So that's the inside of a polygon. And already we see the inside of a polygon as a slightly sophisticated object, because it's taking two positive things. The c's mod GL1 are positive. The z's, see, this isn't really strictly right. I'm not modding out by GL3, but anyway, they're positive matrices. Okay? The c's are positive, the z's are positive, and I take a positive combination of positive external data to define a region that lives inside the two-dimensional projective space, just 2 dimensions, or G13. Okay. Now, I just motivated thinking about the inside of the polygon. We were familiar with polygons. But there's maybe a deeper reason why we should impose these positivity constraints. Let's say I just have the idea that I want to take some linear combination of external data. So the z's are fixed, and I'm going to scan over a bunch of c's and see what kind of region it gives me. You see, if I want to write down a formula like this and have it make sense as a projective statement, it must mean that there's no way I can hit 0 on the left-hand side. Okay? 0 wouldn't be in the projective space. But if I have enough z's, in fact, if I have 4 or more z's, there's always some way of taking one z and writing as a linear combination of the other guys. And so I'll inevitably hit 0 on the left-hand side. So I have to do something to avoid 0. Well, what do you have to do to avoid 0? You have to make things positive, right? So that's what positivity is doing. The positivity of the c's and the z's is ensuring that this is a projectively well-defined statement. Okay. All right, now there's more. There's a little more about this I can say in detail, but let me not go through this in great detail. Perhaps I'll just say very quickly that if you write y as some linear combination of the z's, this is a two-dimensional space. the space of all the C's is very high dimensional. So this is a highly, highly redundant covering of the inside of the polygon. You can go down to the two-dimensional cells of this external G1n, this external positive, the positive space of the C's. You can go to the boundaries of this space where you set many of the C's to 0. In fact, all but 3 of them to 0. And that will give you, the image of those under this map will give you all the various two-dimensional triangles in this picture. Okay? So the various two-dimensional cells of the internal G1n map into all the different triangles in the picture. And of course, we could just take the union of all the triangles that cover the inside, but there are nicer things that we can do too. We can, for example, triangulate in this way to cover the inside of the polygon nicely. Okay. And there's a final concept, which we're familiar with both with triangles and polygons, which is their area. Okay, so we can think about the area of a triangle or a polygon. So this is really, if we think, gosh, these people all went to work simultaneously. Okay. Let's say we want to talk about the area of the inside of a, well, the area of a triangle. If you think in a projective space, there is no area. Area has units. So we have to define a line at infinity in order to define the notion of an area. And in fact, if you just give me a triangle, you just draw 3 lines in a projective space. There's 4 triangles in that picture. You don't even know which triangle you're talking about. So you draw a line at infinity, and that line passes through all the triangles but one of them. And you're talking about the area of the triangle that it's not piercing. Okay? Or if you talk about the dual points, if you replace points with lines, then if I have points and I want to talk about the inside of the triangle, then I also have to give some other privileged point y, and the triangle that I'm talking about is a triangle that y is inside of. Okay? Now, if you do that, we have the usual notion of area, which has units and is not a nice projective, is not a perfect projective notion, but there's a closely related, so this formula, you might not find it familiar, but that's just the junior high school formula for the area of a triangle. Okay? So it's not a projectively well-defined notion, but there's something closely related to it, which is a certain 2 form. Certain 2 form now on this y space. So y in our picture was just the point at infinity, or the line at infinity. And normally we think of infinity as fixed, and maybe we move all the points around. But now we imagine all the points as fixed, and we move the line at infinity around. Okay? We move the point at infinity around, and we imagine this as a form in that space. So the area is closely related to a form in this space, which has the unique property that it has singularities when y hits the boundaries of the triangle, and has the simplest possible singularities. The simplest possible singularities are these so-called logarithmic singularities that looks like dx over x, dy over y. Okay? Okay, so this is it's maybe slightly less familiar way of thinking about area. There's the familiar way of thinking about area, and there's this notion of a form with logarithmic singularities on the boundary of the region that you're talking about. And that notion of a form generalizes from a triangle to a general polygon here. Okay? All right, so those are all the things that we're familiar with triangles and polygons. So now we're going to lift the whole story into the Grassmannian. Okay? So instead of having one y, in general we'll have k y's. We're going to have the external data. Before we imagine these external data lives in P2, so there are 3-dimensional vectors modulo rescaling. Now we imagine that there are just higher dimensional vectors. Okay? In general, this could be any even integer, but for physics purposes, it'll have to be 4. So the external data will be associated with 4 plus k dimensional vectors up to rescaling. And they're positive in the sense of all the minors, ordered minors being positive. And we take a positive linear combination of this positive external data in order to give us the lift, the analog of the notion of the polygon in the Grassmannian. In GK, in general, GK, k plus anything even, for physics, we'll need GK, k plus 4. Okay? So that's it. That's the complete definition of the Amplituhedron. Okay? It's this part of GK, k plus 4. Okay? The positive combination of positive external data, all the ordered minors of these C's are positive, the Z's are fixed. You scan over all the C's such that all the ordered minors are positive, and that carves out a region in GK, k plus 4. that 4 is related to the 4 spacetime dimensions. But if you replace it with any m, you don't get a theory that corresponds to any theory that we know of in higher and lower dimensions. Instead, what you get is a theory where the symmetry is not SL4, the conformal group in 4 dimensions, but is SLM. Okay, so it's another kind of generalization. It doesn't have the Lorentz symmetry of higher dimensions, but it has this funny conformal symmetry. In fact, the higher dimensional theories, well, maybe I'll say it very quickly now. The higher dimensional versions are things, see, this m equals 4, which, when you understand a little bit more about the geometry, is really the minimal possible case, okay? M equals 4 is really the very, very minimal possible case. But if you go to higher m, they correspond to things that don't factor like this, but factor in 3s. That's m equals 6, or factor in 4s. That's m equals 8, and so on, okay? So they're not Lorentz invariant local theories, but they're theories that have the Yangian of SLM, or SLM/m as their symmetry, and the factorization properties that are somehow generalizations of those that we're familiar with in standard field theory. Okay, so that's the simple mathematical definition of the amplituhedron. It's the inside of a polygon generalized to the Grassmannian. And the tree amplitude is, in an appropriate sense, the volume of this region. And some of the simplest ways of triangulating this region correspond to the computation of the tree amplitude using the BCFW recursion relations. Okay, well, okay, I don't have any, these are all technical things. I don't have time to explain them in any detail. But perhaps one thing that you've noticed is that everything I've been talking about is completely bosonic. And normally when we have supersymmetric theories, we have supergeometry. So here, we don't have supergeometry. We have completely bosonic geometry. And out of this bosonic geometry, there's a way of extracting superamplitudes. That's rather different from what we're sort of normally used to with geometry in projective space P3/4, for example. Here, instead of P3/4 supergeometry, it's bosonic geometry in P3 plus K in the sector that has K etas in it. The Z's are augmented to higher dimensional bosonic variables, the ordinary 4 variables that we talked about, and K other ones, and these are treated in some appropriately infinitesimal way in order to extract superamplitudes from it. Okay. Let me just say one more thing before I wrap up. So I just defined this object, right? So I think, so at least according to the rough goals, it's clear we didn't talk about a Lagrangian. We don't have anything that looks like gluons. We don't have any of that stuff. I didn't use the word factorization. I didn't talk about things going on shell, and so on. So how, if you were just exploring this object, would you start getting a hint that it should correspond to things that are local and unitary? Okay? And the way, even purely mathematically, you would start understanding this is to do something very natural, which is to explore what the boundaries of this space look like, right? It's like when you have the polygon, the first thing you notice about the polygon is that the edges are the lines 1, 2, 2, 3, 3, 4, and so on, okay? So you just want to see what the boundaries look like. That's something which is very interesting. It's not obvious, totally obvious. It's a small argument, is that the first boundaries, the codimension 1 boundaries of the amplituhedron, are the ones on which this k-plane in k+4 dimension y contains the following plane: zi, zi plus 1, zj, zj plus 1. Okay? That's the analog of the fact that for the polygon, the boundaries are 1, 2, 2, 3, 3, 4. Here, the boundaries are labeled by 4 z's and not 2 z's. And instead of being 1, 2, 2, 3, 3, 4, they're ii plus 1, jj plus 1. And then by studying the consequence of positivity, you actually discover that as you approach this boundary, the amplituhedron splits and really geometrically factorizes into 2 lower amplituhedra. It splits in precisely such a way as to reflect this picture, okay? Which is, of course, exactly what we think of as what an amplitude does as you approach a factorization channel. Okay? Now, under the rules, going to the boundaries of the amplituhedron correspond to exploring the singularities of the scattering amplitude. That should be fairly natural. And so we see that just the geometry of positivity first puts the boundaries in the correct spot, and secondly, makes it factorize on the boundaries exactly as scattering amplitudes should. Okay, so I won't have time to talk about this, but as I just alluded to before, there's a simple picture for hiding particles that motivates an extended notion of positivity. And with that extended notion of positivity, it's essentially exactly the same structure. This extended notion of positivity dot positive external data, which goes from computing trees to computing loops. And the generalization of the story we had before of exploring the boundaries finds one new kind of boundary, which corresponds to what we're used to, cutting an internal propagator and the sort of factorization that we're used to with unitarity. Okay. Something else that we are hoping to see from a picture like this is that the symmetries of the problem, the fact that it's local and unitary are not completely obvious. You have to work a little bit to see that it's local and unitary. But the symmetries should be obvious. And the symmetries indeed are very obvious in this picture. In fact, this is a rough statement, but there's a very obvious symmetry which are diffeomorphisms that just keep you inside the positive part of the Grassmannian. And those positive diffeomorphisms are the origin of this infinite dimensional Yangian symmetry. So the symmetries are actually obvious in this picture. All right. So this is now an example, at least in this very baby toy planar n equals 4, the simplest possible problem. There is an example of the sort of thing that we're after. It's a very simple mathematical structure that gives, in this limit, it's complete and autonomous. That's the important thing from our point of view. Definition of all the scattering amplitudes without any of the usual language. No Feynman diagrams, not even recursion relations on shell processes, and so on. All right, let me skip over these examples. Okay. Just to give everything I said was rather abstract. The amplituhedron in general lives in a high-dimensional space. Even the tree amplituhedron lives in a 4k-dimensional space. So if you want to talk about the simplest amplitudes with 3 negative helicity gluons, that corresponds to k equals 1, even there, they're 4-dimensional. The next case, they live in an 8-dimensional space, and so on. So it's a little bit hard to visualize. But in some cases, we can visualize lower-dimensional faces. So this is a pretty misleading picture in many ways because the actual object, it doesn't have flat faces like this. It's curvy. So this is a particularly simple version. But this is a 3-dimensional face of the amplituhedron. And if you give me the external data for 8 gluons, from that external data, I can construct the positions of these vertices. And the amplituhedron is the inside of this shape. Okay? The volume of that calculates the tree amplitude for that particular helicity at the LHC. So the leading part of this particular helicity component of the scattering amplitude at tree level is the volume of that thing. Of course, this is hundreds of pages of Feynman diagrams. Okay? Now, people have been computing these things using Feynman diagrams for ages. Okay? So people have known how to compute this using BCFW recursion relations for many, many years now. What we now see is that if we compute using BCFW recursion relations, there's many different ways of writing the answer, but one of them involves a sum over 4 terms. Those 4 terms are now interpreted as the volume of that little tetrahedron, that little tetrahedron, that little tetrahedron, and that little tetrahedron. Okay? And then all the other ways of writing it using recursion relations are just different ways of triangulating exactly the same object and breaking it up in tetrahedra in different ways. Okay. Now, the final quick thing I'll say is that if you wanted to proceed to explore this geometry more systematically, the first thing that you'd want to learn how to do is how do you build these positive matrices? Remember, these coefficients, I'm sweeping, I give external data and I'm sweeping a region of the Grassmannian given by these coefficients, which are positive combinations of positive external data. How do I make those coefficients positive? How do I make these matrices with all the minors are positive? That seems like a nice, well-defined mathematical problem, and our mathematician friends found a beautiful answer to it, which is that you do it gradually. You don't try to make a big positive matrix all at once. You start with a matrix which is the identity in 0 everywhere, and then you gradually deform it, one step at a time, slowly by slowly by slowly, by using rules such that at every moment it's obvious that you're making all the minors positive and more positive. Okay? It's non-trivial that you can build all of them in this way. Now, what's quite beautiful is what they found is that this procedure for building the matrix is encoded by drawing a planar graph with black and white vertices. Okay? And once you draw a picture like this, it gives you a particular way of building a matrix. That picture looks an awful lot like gluing together 3 particle amplitudes for a space-time scattering process where every particle that appears is on shell. And in fact, it is. There is a one-to-one correspondence between this way of gradually building up positive matrices and getting an on-shell space-time picture of what is going on. Okay? So this is the connection between on-shell scattering processes, and which give us the building blocks for the scattering amplitude, and the positive Grassmannian that had already been found a number of years ago. The new thing that we've learned with the Amplituhedron, these are building blocks. And now we know how these building blocks, or why we're putting these building blocks together in the particular way to get the whole amplitude. What they're doing is triangulating the Amplituhedron. Okay, but this is the way, again, pursuing the mathematical question, the natural mathematical question, you start seeing that, that what's going on can be associated with a space-time, at least an on-shell space-time scattering processes. Okay, so that's my conclusion. So we've seen that the amplitude can be thought of as the volume, should be in quotes. I didn't really have time to explain that way, but roughly speaking, the volume of the Amplituhedron. We can break it up in many ways. We can triangulate it in many ways. Each triangulation is associated with a certain space-time scattering process. The pieces by themselves don't have a local or unitary interpretation, but the final result is local and unitary, and the fact that it's local and unitary is a derived fact. Okay. So there's obviously many open issues. The biggest one that bothers us is that everything has been defined perturbatively. So if you want to know what's going on L loops, the L loop integrand for the scattering amplitude is associated with the volume of the Amplituhedron. But we don't yet have a non-perturbative question to which the full amplitude is the answer. Okay? Associated with this is that this what I referred to as the volume is just this form that I was mentioning before that has logarithmic singularities on the boundary of the Amplituhedron. So we can define what the form is. That's what it is. It's a form that has logarithmic singularities on the boundary of the Amplituhedron, but we don't have, at the moment, any efficient way of calculating it directly without triangulating the space. And that seems bad. It would be good to have a direct definition for what it is. My guess is that finding that would make it much easier to go from this Gates theory description of the physics to the string dual description of the physics, but we'll see how that works out. Okay, obviously, going to less supersymmetry is a big direction a number of people are pursuing. Just one thing I'll say is that this connection between on-shell scattering processes and the Grassmannian is actually universal. It has nothing to do with n equals 4 super Yang-Mills. It just has to do with this picture of gluing together elementary 3-particle processes to make more complicated processes. N equals 4 super Yang-Mills is particularly special for having the simplest possible form associated, the simple possible answer associated with these on-shell processes. But the connection between the on-shell process and the Grassmannian is general, and so one can hope that theories with less supersymmetry that have, in addition to all of this infrared physics and factorization and all the things that we're familiar with at long distances, also ultraviolet singularities will find a natural interpretation in the Grassmannian. Okay, so let me finish. We started talking about QFT, as you all know, field theory and string theory have had many backs and forths over the last 40 years, where one killed the other for a while until we're now all happy and agree that they're the same thing. Okay, but I think one of the feelings that a lot of people have had, especially since ADS-CFT, is that actually, in a sense, QFT may have returned. This isn't the universal feeling, but it's a sense that you sometimes get talking to people, that it's really the QFT that's king, right? The field theory is perfectly well defined. That's king. We know what it is. We know what it is at weak coupling. We can put it on the lattice. We know everything about it. And then somehow, miraculously, at strong coupling, tuck, gravity, strings, everything comes out on the other end. Okay? So that field theory is the answer to the question, what is string theory? But I think given that we understood perturbative field theory for a long time, we didn't understand strong coupling dynamics of field theories at all. Then we started understanding them, and they were miraculous. There were gauge-gauge dualities, gauge-gravity dualities. And at first, the number of miracles was small. I think it's fair to say that today the number of miracles is bigger than the number of ordinary things about quantum field theory. Okay? So when the number of miracles is bigger than the number of ordinary things, it makes you think there must be a different way of thinking about what it is, which doesn't make the miraculous things seem so miraculous. And most of the miracles, and in a sense the sharpest miracles, are at strong coupling. But all of this wonderful structure at weak coupling is another hint. It's going 60 years back to the very home base of quantum field theory, good old-fashioned perturbative amplitudes. Even there, there is obviously something being hidden by the standard way of thinking about things. So at least I think it's more likely that this is the picture, that there's really something else. Okay? There's something else which in one limit can be shown to reproduce things that look like field theory, and another limit will look like a familiar string theory, but there's something else is what we should be looking for. All right, thanks a lot.